So Curie was working on finding different radioactive elements. Ernest Rutherford, we learned about in Chem 1A, and other researchers were looking on, well, what is this radioactivity? What are its characteristics? So they found that the nuclei, just plural of nucleus, the nuclei of radioactive elements are unstable. And so they'll spontaneously decompose. And in that process, they will emit small particles. And they do that because that makes them more stable. So those little pieces are radiation, radioactivity. And there are different categories. There's alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. And we'll talk about all three of those. Before we do that, let's review nuclear symbols, which we learned in Chem 1A. So a nuclear symbol has an element symbol, and to the left there's a stacked superscript and subscript number. On the top is the mass number, and on the bottom is the atomic number. The atomic number is the number that's on the periodic table, the number of protons. The mass number is the total number of protons and neutrons in the nucleus of that atom. So if we want to know the number of neutrons, we can take the mass number and subtract the atomic number. The A and the Z thing, those get kind of confusing. So the way I like to think about this, let's get some of that out of the way. So we've got A and Z, and these are stacked up conveniently so you can subtract them. So the bigger number is always going to be on top and the smaller number on the bottom, and you take this minus that, and that will give you the number of neutrons. Most elements have different isotopes. Some have 2 isotopes, some have 3 or 4, some only have 1, and you don't get any of that information on the periodic table. When we're talking about a particular isotope of an element, we often refer to that as a nuclide. Nuclide is just one kind of isotope. So we can represent isotopes by the element name or the element symbol followed by the mass number or with a nuclear symbol. So the nuclear symbol for carbon-14 is that. This could also be called C14 or carbon-14. The main subatomic particles also can be represented with nuclear symbols, so proton, neutron, and electron. A proton has a mass number of 1, because the total number of protons and neutrons is 1, and the number of protons is 1, and the symbol here is a lowercase p. These are lowercase letters because we don't want them to be confused with phosphorus and nitrogen. For a neutron, the mass number is 1, because total number of protons and neutrons is 1, and the atomic number is 0, because a neutron doesn't have any protons, right? So far, everything is, I think, making sense. And then we have an electron, so E for electron. Mass number is 0, no protons or neutrons. But the number of protons is -1. So, weird. We'll see where that comes from in a couple minutes. Okay, so the first type we're going to talk about is alpha decay. And here, an unstable nucleus is going to emit a particle composed of 2 protons and 2 neutrons. 2 protons and 2 neutrons is the same as a helium nucleus. A helium atom also has 2 electrons, but if you don't have the electrons, it's a helium nucleus. And so this is given the symbol He, mass number of 4, atomic number of 2. That is the symbol for the alpha particle. So we have this unstable nucleus, and it just spits out this particle of 2 protons, 2 neutrons. Now, the question of why it does that is, I don't know if anybody understands that yet, but it happens. And that's all we care about right now. Any questions? So we can write a nuclear equation to describe nuclear processes like radioactivity. So these equations are going to be similar to molecular chemical equations in that we're going to balance them, but they're also a little bit different. So here's an example of a nuclear equation. On the left is the reactant, and this is called the parent. So that's the parent nuclide, and this is going to spit out a particle. Here it's spitting out an alpha particle, and then it turns into something else. This is called the daughter. So the parent was the source of the daughter. And we're not balancing letters like we did before. We have a U, a TH, an HE. That's not balanced at all because in nuclear reactions, elements often change their identity. So here, uranium is changing into a different element. That only happens in nuclear chemistry. So we didn't, kind of glossed over that in Chem 1A. Conservation of mass, conservation of energy says you can't do that. But those said in a chemical process, not in a nuclear process. In nuclear processes, this happens. So in nuclear reactions, elements often change their identities. So what we're balancing instead of the letters is the numbers. The mass number on this side is 28, and the sum of the mass numbers on the other side, 238, the sum of the mass numbers here is the same, 238. The atomic number here is 92. The sum of the atomic numbers there, also 92. Right, the nuclear equation for the alpha decay of polonium-216. So this is something we should be able to do, say, for an exam question. So we're going to start by writing the nuclear symbol for polonium-216. So PO-216 is the mass number. How do we find the atomic number? Periodic table. So there's Po. Remember the Teletubbies? Oh, yeah, they're so cute. Po is element number 84. Periodic table tells us 84 protons. The problem tells us this one has a mass number of 216. We could figure out how many neutrons by subtracting here, but we don't need to do that. So let's not, right? This is going to undergo alpha decay, because that's what they're telling us it does. So we're going to have the daughter nuclide here. I'm just going to leave a space, and then I'm going to write the symbol for the alpha particle over here. And so that is something you need to learn, the symbol for the alpha particle. It's a helium nucleus. So now what we're going to do is we're just going to look at the numbers. So for the mass number, I have 216 on the left, and I have an unknown, and I have 4. What does the unknown thing need to be so that the total here is 216? 212. So that one's 212. And then we do the same thing with the atomic number. We've got 84, don't know, and 2. So this one is what? 82? 82 plus 2 is 84. This 82 tells us what element it is. So we go back to the periodic table. 82 is lead. So Pb. So in this nuclear reaction, an atom of polonium turned into an atom of lead. Any questions? Yeah.
Does the alpha particle stay consistent in like all alpha decay processes?
Yeah. This will be the symbol for the alpha particle always. Yep. Any other questions? Mm-hmm.
Is this basically kind of looking like alchemy in a way?
Yeah, actually it is. So the question was, is this basically low-key like alchemy? Yeah, it is. So alchemy, people long time ago, before they realized it's kind of possible, but not really possible. They were trying to turn things like lead into gold, right? They did all kinds of things. A lot of stuff involved collecting a bunch of urine. It's just, you can read about it, it's crazy. People devoted their lives to trying to change things into gold, and none of them were successful. So it turns out you can turn things into gold through nuclear processes, but it's absolutely not cost effective. Yeah, you spend way more money making it into gold than just going out and looking for gold or buying it, the stock exchange or something. But that's a great question. Yeah, this is alchemy. Yeah.
So usually the gold is found, like,
Yeah, gold is found. Gold is very unreactive, which, if you go look at it on the list of standard reduction potentials, right, it does not reduce easily. So we find it as gold. You can find big chunks of it sometimes. Other things like iron react with all kinds of stuff, and so you don't find just iron, you find compounds containing iron ore. And then you have to, get the rest of the stuff out of them. But silver and gold are things that can be found as the elements. Yeah. So we're going to learn some of the characteristics of the different types of decay. One of the things we're going to talk about is penetrating power. Did I forget? Oh, yeah, I missed something. Okay. So alpha radiation is the 18-wheeler truck, the semi-truck of radioactivity. We're going to use a vehicle analogy. We'll be comparing some to semi-trucks and some to cars and some to motorcycles. So this is the truck, because it's the biggest of the particles. It has high ionizing power and low penetrating power. So what do we mean by that? Ionizing power is the ability to ionize other molecules or atoms. So this helium nucleus, the alpha particle, crashes into something else. Many times it will ionize the thing that it crashed into. And this can be very damaging in a living organism because you have all these chemical reactions that need to occur. And if you crash into something and change it from an atom or a molecule into an ion, it's not going to react in the same way. And so you're messing up the chemical reactions. This can result in cells dying, the organism dying, or the cells reproducing abnormally. So that's ionizing power. Penetrating power is the ability of radiation to penetrate through matter. So radiation has to get into a cell to cause damage. If it can't get into the cell, it can't do any damage on the inside. So alpha particles have the lowest penetrating power because of their large size. And here's where this vehicle analogy helps us. So we can think about vehicles in a traffic jam. You've all been in traffic jams, right? You're out on Highway 41 and just nothing's moving and you're like, right? Well, if you're driving a semi-truck in a traffic jam, you're just in a bad situation, right? You cannot weave back and forth and get through. You just can't penetrate through that traffic jam. You're just stuck, right? So alpha particles are like that. They're really big. They cannot get through the traffic jam. They can be stopped by a sheet of paper, by clothing, even by a gap of air. So you can stop these particles from entering things very easily. So outside the body, they're pretty safe. They really can't do much of anything to you. But if you ingest them or inhale them, now they're inside your body, and then they can do a lot of damage because of the high ionizing power. Any questions about that? The next one is beta decay. These are named for Greek letters, alpha, beta, A and B. In beta decay, we have an electron that's getting emitted from the nucleus. Are there electrons in the nucleus? Are there electrons in a nucleus? No, there aren't. The electrons are outside the nucleus. So how can you have an electron come out of the nucleus? Okay, so this is kind of trippy. A neutron can change into a proton and an electron. It can do that. So what happens in beta decay is you have one of the neutrons splitting into a proton and an electron. The proton stays in the nucleus and the electron gets shot out. That's the beta decay. So neutron becomes a proton and the leftover is an electron that gets emitted. So this is why electrons have a -1 atomic number in their symbol, because the numbers have to match up, right? So 1 equals 1 plus 0, 0 equals 1 plus -1. So here's an example of radium decays to actinium by emitting a beta particle, an electron. And so we look at the atomic numbers, 228 and here 88. This is -1. And so then we can predict this because this plus that needs to equal 88. Any questions? Characteristics of beta radiation. Beta radiation is like a car, four-door sedan. Less massive than an alpha particle, so they have, excuse me, sudden dry throat. Because they're less massive, they have lower ionizing power. So ionizing power is like damage in a collision. So a semi-truck runs into something, it's going to cause a lot of damage. Right? A car runs into something, it's going to cause damage, but not as much, because it's just not as big, right? So these particles will ionize things, but not as much as alpha particles. But because of their smaller size, they have higher penetrating power. So you think of the traffic jam. The semi-truck is just kind of stuck. He can't change lanes or anything. But a car, it's difficult, but you can change lanes and maybe get through a little faster than the rest of the people, right? So beta radiation can be stopped by a sheet of metal or a thick piece of wood, but like your clothing or a piece of paper, it's going to go straight through that. So beta radiation is more dangerous outside the body because it can penetrate into the body more easily, but it does less damage if ingested than alpha particles. Gamma ray emission is just electromagnetic radiation. It's not particles. We learned about the electromagnetic spectrum in Chem 1A, and it starts with radio waves and goes through visible light, and then it went to ultraviolet and X-rays, and gamma rays were way at the high end. This is very high energy photons, high energy electromagnetic radiation. So these are rays, they're waves. They have no charge, they have no mass. And so the mass number, the atomic number are both going to be 0 because they don't change for the nucleus that's undergoing this. So the symbol is the Greek letter gamma, 0, 0. So this is just a wave that comes off, energy. Gamma rays usually get emitted along with other types of radiation. And you can't just predict what's going to emit gamma radiation by looking at a chemical equation, because the gamma ray doesn't affect anything. So this is sort of typical of gamma ray emission. Here we have uranium decaying to thorium by alpha decay, and along with the alpha decay, we also get gamma ray emission. So gamma rays are like the motorcycles of radioactivity. So they have the lowest ionizing power. When they crash into things, they do the least damage. But they can get through stuff. So, traffic jam, there's a guy on his motorcycle, and they can drive between stopped cars, right? It's actually legal. You can do that. You're not supposed to go through slowly moving cars, but if everything is stopped, you can do that. So these things are hard to stop. It takes several inches of lead shielding or thick slabs of concrete. So if you're, worried about nuclear war and, want to build a fallout shelter to protect yourself from nuclear fallout, you need it to be very thick walls of concrete, or gamma rays are just going to come in there and get you anyway. Honestly, if we had nuclear war, we've got way worse things to think about than whether individuals were exposed to radiation. That's actually one of the least of the worries. A positron is another particle. This one doesn't have a Greek letter in its name. The positron is the antiparticle of the electron. You've probably heard of matter and antimatter. And when matter and antimatter come together, they just turn into nothing. That's real. A positron is the antiparticle of the electron. If you get a positron colliding with an electron, those two particles annihilate each other and release energy in the form of gamma rays. So positron, electron, they both end with tron, right? We should know, just because we've used them for so long, electrons have a negative charge. A positron is a positively charged electron. So what happens here, in positron emission, we've got a proton in the nucleus that breaks into a neutron and a positron. We just learned that a neutron could break down into a proton and an electron. A proton can break down into a neutron and a positron, and the positron gets spit out. The positron has a nuclear symbol very similar to the electron, except this is positive instead of negative. This positive here is not related to the charge. Positrons are positive and electrons are negative, but the sign here is so that the mass numbers and the atomic numbers work out. So here, a proton becomes a neutron. Well, the atomic number goes from 1 to 0, so the positron has a +1 atomic number so that these things work out. So when an atom emits a positron, the atomic number goes down by 1. An alpha particle makes the atomic number go down by 2, and a beta decay electron makes it go up by 1. So here's an example. Phosphorus 30 becomes silicon 30 by emitting a positron. Positrons are a lot like electrons. They're the antiparticle, right? So same ionizing power and penetrating power as an electron. That is the four-door sedan, right? And this last one is not the emission of a particle, it's the capture of a particle. So electron capture. A nucleus will assimilate an electron into itself. Where does the electron come from? Well, it's from one of the inner orbitals, like the 1s or 2s orbitals, those ones that are really close to the nucleus. Why does this happen? That's beyond the scope of this class. It's very mysterious. It does so to lower energy. It's just very complicated. Yeah. Yeah, this is getting into the quantum level of things. Yeah. which a lot of people find very, very fascinating. And a lot of other people find it just mind-bogglingly confusing, and they just don't want to even think about it. And yeah, both opinions are valid. Because I mean, up until now, it's like, well, we had protons and neutrons and electrons, and you could rearrange those, you could give the electrons or share them and stuff, but everything was nice. And now I'm telling you that, well, protons can turn into neutrons, and neutrons can turn into protons and electrons, and it's like, what? And then the positron meets an electron, bang, it disappears. Very weird stuff, right? So what happens here with electron capture is one of the protons in the nucleus combines with this electron that got captured to make a neutron. And this is the opposite of this one, right? This was emitting an electron. Neutron became a proton and an electron. In electron capture, we have a proton capturing an electron to become a neutron. So in one sense, it's really, really confusing, but in another sense, we've got these nice little simple equations, and we're just doing things like 1 plus -1 is 0. So here, the atomic number of the element decreases by 1. So ruthenium captures an electron. The electron is a reactant, not a product, because it's not getting spit out, it's being taken in. And we predict the product in the same way. 92 plus 0, so this must be 92. 44 minus 1, this is 43. Look on the periodic table, and the symbol is Tc. Any questions? This is a table in your textbook summarizing all of this stuff. And you're probably wondering, what do I need to remember? Do I need to memorize this whole thing? No, you don't. You need to know the nuclear symbols for the different types of radiation. Alpha particle is a helium nucleus. You just kind of have to memorize that, right? Beta particle is an electron. And then the symbol for the electron, well, it's an E for electron, and the mass number is 0 because electrons basically have no mass. And this number here is negative, not because the electron is negative, but we can remember it that way, right? Electrons are negative, and so that one's going to be a -1. Down here we have the positron emission. Positrons are like the opposite of electrons, and so the symbol is very similar, but it's a +1 instead of a -1. Gamma radiation is just the letter gamma in zeros because this is not a particle at all. Electron capture, there's our electron again, but instead of getting spit out, it's being captured. Okay, so you need to know those things. You need to be able to complete nuclear reactions. And you need to have an idea of the relative penetrating power and ionizing power of these different things. So this is the biggest one. This is the semi-truck. Can't get through a traffic jam very easily, but when it hits something, it does a lot of damage. Low penetrating power, high ionizing power. Here's an electron. This is smaller. This is like the car. A car can kind of get through, and it does some damage. So this is intermediate in ionizing power and penetrating power. The positron particle is going to be the same. And then we have gamma radiation, and this has no mass. So this is like a motorbike. It can just go straight through most things, but has the lowest ionizing power. So those are things you need to know. You might need to make yourself some flashcards. Okay, so we're going to practice writing nuclear equations here. For this first one, write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235. That's followed by beta decay of whatever that daughter nuclide was, and then alpha decay for that one. So what I want you to do is work on writing the equation for the alpha decay of uranium-235. Okay, so let's talk about this. The first thing we need to do is the symbol for the parent, uranium-235. So capital U, and the mass number is 235. What is the atomic number? 92. And this is going to react, and it says alpha decay. So the particle is going to be an alpha particle, He42. And then to figure out this guy, we're going to look at the numbers. So here I have 235, and here I have 4, so I need 231 in there, right? And on the bottom, this side's 92, and I have a 2, so I need a 90, yeah? And 90 is TH. Anybody have any trouble with that one? So the next one then, we're going to take this guy, TH, 231, and that's going to decay by beta decay. Do you need some time to work on that one, or did you already get started on it? Everybody good? Okay. So what is the particle that's getting spit out? What's the symbol for it? 0, -1, E, right? So that's something you have to memorize. Beta decay, you write that in. The rest of it, not too hard, right? So this is also 231. This is 90, and so here, 90 and, something and -1. So this must be 91, so that these add up. Now, this math is simple enough that we should be able to do it in our heads, but then sometimes our heads are foggy. Feel free to use a calculator. There's no shame in that. 91 is PA. And then it says another alpha decay. So we take that one, PA 91. So alpha decay, we've got the helium again for the alpha particle. And then here 231, what plus 4 is 231, it's 227. And I need 91, so this one must be 89. And 89 is AC. Any questions? There will be questions like this on exam 4. Okay, let's do these. Nuclear equation for positron emission of Na22 and electron capture in Kr76. Okay, let's do these together. Sodium 22. So we got sodium 22. What's the atomic number? 11. Positron emission. We've got an arrow. And so what's getting spit out? 0 plus 1 E. It's the anti-electron. And then we balance the numbers. So 22 here, that one's 0, so this must also be 22. This is 11, and so over here this is 10, and that's neon. Any questions? Electron capture. So here we've got krypton, 76, And what's the atomic number for krypton? 36. Electron capture means we're adding an electron. So electron is E, and the negative one. This one's easy because we're just adding instead of figuring out by difference. So this must be 76, and this one must be 35. That's what bromine. Any questions?
Why do you use the gamma?
When do you use the gamma? That's a great question. When do you use gamma? When the question tells you to.
What is the benefit of it?
Pardon me?
What is the benefit of it? Why do we use it since?
Well, so this one might say, write the nuclear equation for positron emission of this, so accompanied by gamma emission. So if they told you accompanied by gamma ray emission, then you would draw the gamma symbol here also. Yeah. It doesn't affect the mass number or the number of protons, but it's energy that's getting released. And so it is actually really important, but it doesn't seem very important in the nuclear equations. So you would put that in there if they told you there was gamma ray emission. Otherwise, there's no way that you would be able to tell ahead of time whether there would be gamma ray emission or not. Any other questions?